Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In today's lecture, we will have a comparative account of the quantum mechanical models we have discussed so far. So far, we have seen quite a few quantum mechanical models and have obtained exact solution of these quantum mechanical models. While we are discussing a model by itself, we are focused on that particular problem, but in today's class what we will do is that we will have all the models at a glance, and then we would see how the systems are different, where are the possible applications of this system, and how the solutions are different, and is there a common story behind them. This is the topic of today's discussion. Just to remind you, we have discussed quite a few quantum mechanical models and we solved them exactly. The first problem that we took up was particle in a box. Here we defined a particle with certain mass which was restricted to a particular region of space. While discussing this problem, we emphasized that particle in a box is quite an useful problem, because any atomic or molecular system you see, they actually represent particle in a box problem, because an atom has an electron which is confined to the nucleus. In a molecule, there are groups of nuclei and then there are a bunch of electrons. The electrons are confined to this box created by the nuclear environment. So, molecular systems per se can be represented as particle in a box, where the particle is an electron which goes around the box, that is the molecular environment. Of course, we dealt with this system by considering only one particle and we neglected the interaction of this particle with other particles. So, that way the problem that we solved was simple than a typical molecule that we have, but in several cases we can actually see where the conjugated ions are there. So, there the pi electrons and sigma electrons are separable. So, we can treat, for example, delocalization of pi electrons effectively with a particle in a box kind of problem. The next problem that we dealt with was harmonic oscillator. While particle in a box showed the translational motion of a particle, with harmonic oscillators we could discuss about the vibrational motion of a molecule. We can use harmonic oscillator model for any system which responds to an external field and then gets disturbed from its equilibrium position, but it goes via this equilibrium position in a to and fro motion. So, in all such cases we can use harmonic oscillator, but for molecular systems, molecular vibration is an important field where harmonic oscillator solutions are heavily used. The next three problems are in a way related to each other. They are particle on a ring, particle in a sphere, or rigid rotor. These three systems are related to each other because all these three systems show a rotational movement of a particle. For example, particle in a ring, it shows rotation on a plane, on a ring. Particle in a sphere shows rotational motion on a sphere, on the surface of a sphere, and rigid rotor shows rotational motion around this bone. Now, these three problems we could solve by invoking the spherical coordinate systems, and in particular we discuss angular momentum operator to discuss the solution of this problem. The final or the most complex problem that we handle is the hydrogen atom problem. Here one electron which goes around the nucleus, so therefore there is an angular motion possible there. But unlike particle in a ring or a sphere or a rigid rotor, the distance of this electron from the nucleus, that means the r, the distance between the nucleus and electron, that also is changing. So, that is how hydrogen atom is different from the other three angular examples we have discussed. So, now what we will do is that we will discuss some features of these problems. Consider the particle in a box. First problem that we first thing that we will discuss in today's class now is that whenever we have a quantum mechanical system to solve, we start with the Hamiltonian of the system, because Hamiltonian is the thing that we know about the system, and this Hamiltonian operator is our starting point. So, it is very important that we see or we are able to write the Hamiltonian, because this is the first thing that as an user we provide for this system. For example, when I have a particle in a box, the Hamiltonian, since I have a single particle, so which shows some kinetic energy, and I write this kinetic energy as the usual kinetic energy operator form plus the potential energy. But we kept the potential energy 0 within the box and potential energy infinite outside the box. So, this potential energy is either 0 or it is infinite, depending on whether the particle is within the box or whether the particle is out of the box. So, therefore, when V is infinite, so we saw that the wave function would vanish, because we have huge amount of potential that the system can never cross, and when V equals 0, we actually do not have this term. So, therefore, essentially we discussed about the kinetic energy of the particle or the translational motion of this particle within this box. Now, in particle in a box problem, our potential energy was constant, whether it was 0 or infinite, it was constant across x value. So, this was from 0 to L in the box of length L. Next, we took up a problem, the harmonic oscillator, where the Hamiltonian, so again we have a particle, so whose kinetic energy is again given by d square by dx square. So, we are defining this harmonic oscillator in one dimension, plus there is potential energy, and this potential energy is the harmonic potential half k x square, where k is the force constant corresponding to this oscillator. Now, this form of the potential energy gives rise to this potential, the harmonic potential. Of course, we can for other systems, wherever it is necessary, instead of a quadratic potential, we can have a quartic potential and so on, but this is the simple model that we use, the harmonic oscillator model. Unlike particle in a box, here the potential energy is a constant, is a function that keeps changing with the value of x, but then there is symmetry between. So, this is, if it is x is 0, this side is plus, this side is minus. So, it goes from minus infinite to plus infinite, and the potential is symmetric along x, because we have this half k x square in the potential energy term. So, particle in a box represented a hard potential, because we saw a sudden rise of potential from 0 to infinite, whereas the harmonic oscillator problem showed a soft potential, where the potential energy is a varying function along x. Now, these two are the problems that we discussed in terms of linear coordinates along x axis or one coordinate system. Now, we come to the angular motion, where the particle is going around a ring. So, again the Hamiltonian, if I have to write down, so again there is a particle with some mass m. So, I write down a square by 2 m. Now, what I have is particles showing a motion along x y plane, for example, because here I have now two plane, I have to define two axes x y, and I see that when the particle goes around a ring, it actually goes in x and y axis. So, instead of writing down in x and y terms, so I could have written this Hamiltonian as minus a squared by 2 m d squared by dx square plus d square by dy square. Instead of writing it in Cartesian coordinate, what we did is that we changed the coordinate system and we went to a spherical coordinate system, where we had the variables are r, theta and phi, but as long as the particle is moving along a particular value of r, radius r, or so therefore, r is constant, and as long as the particle is going around a ring, that means on one plane, so therefore, theta is also constant. So, I have only one variable which is varying, that is phi. So, the Hamiltonian became h square divided by 2 m square, 2 m r square d square by d phi square, where phi goes from 0 to 2 pi. So, here phi goes from 0 to 2 pi. Now, this is the Hamiltonian. Of course, we said that there is no potential energy that the particle experiences when it goes around the ring. From a ring, we went to sphere by imagining that a sphere is simply a stack of rings kept one below the other, and when the particle is going around on the surface of a sphere, it essentially can jump from one ring to another ring. While it is in one ring, of course, it can show a motion around this ring. So, when it shows the motion around a particular ring, then of course, we know that it is like particle on a ring, but when it jumps from one ring to another ring. So, here in this case what happens among r, theta and phi, we see both, of course, phi is changing. Here theta also changes, because theta is the angle that the point makes with the position vector corresponding to this point makes with the z axis. So, in the similar language, particle in a ring, if I say r, theta and phi, so r is constant, theta is constant, only phi is changing, and in case of particle in a sphere, r is constant, because we are discussing for a particle which is going around a sphere of constant r, where here only theta and phi, these two angular variables are changing. In this case, the Hamiltonian turns out to be, again I could write minus s square by 2 m, then the Laplacian, which is d square by dx square plus d square by dy square plus d square by dz square in Cartesian coordinate, but we have replaced it with spherical coordinates, and in spherical coordinates, when my r is constant, in that case what happens to the Laplacian is, this is simply the Legendre divided by r square. So, that makes our life simpler, because what happens is that when you see this Legendre, this is an operator, so which depends on only theta and phi, whereas the Laplacian operator depends both. Laplacian operator shows differentiation with respect to r, theta and phi, whereas Legendrian shows differentiation only with respect to theta and phi. So, now the advantage of this is that we know minus h square multiplied by lambda square is our L square, which is the angular momentum, square of angular momentum, divided by 2 m square, or L square divided by 2 I, where I is the moment of inertia. So, now what we have obtained here is that the Hamiltonian is a constant multiplied by L square, and we knew the solution of L square. So, we could fit this in. But again, let us continue our discussion. When we go to rigid rotor, for example, rigid rotor, it is a rotor. So, this for example, let us say this is a diatomic molecule. So, this can go rotate in all three directions in Cartesian coordinate. So, therefore, when it rotates in all three directions, you would see that it will create actually a sphere. So, in rigid rotor, what happened is that we had two masses m1 and m2. Here, this is the first example where we discussed about two different bodies, two different particles, although they are connected to each other by a fixed distance. So, that is why we call it rigid. So, it is a rotor which has two particles at two ends, and it can rotate on all three dimensions in Cartesian coordinate, but it can do so while the distance between the two particles is constant, because this is a rigid rotor. So, therefore, while particle in a ring or a sphere or harmonic oscillator or a particle in a box, we always considered a single particle. For the first time in rigid rotor, we consider two particles, but they are fixed, they have a fixed distance. The Hamiltonian of this, you see, when this rigid rotor makes rotational motion, it essentially represents a sphere. So, therefore, the Hamiltonian is no different from the Hamiltonian that we had for particle and a sphere. But one important thing we understood while discussing this rigid rotor is that whenever we have a two body system, we could show exactly that we can express this two body system as two effective one body systems. If you remember, here the kinetic energy of operator corresponding to this rigid rotor would have involved two kinetic energy terms, one each corresponding to each of these two particles. Alternatively, we could write this kinetic energy operator in terms of effective one body problem, where the first one body problem was the translational motion of the center of mass, which could be which is similar to a particle in a box kind of problem. The second problem is the internal motion between the two. So, therefore, we separated the internal and the overall translational motion, and we looked at only the internal motion of this system. So, we had this rigid rotor Hamiltonian. At the end, we came to the hydrogen atom, where the Hamiltonian had, of course, the kinetic energy of the nucleus plus kinetic energy of the electron and plus the potential energy of the electron and nucleus, which is actually a repulsive which is an attractive interaction between the electron and the nucleus, because electron and nucleus, they have opposite charges, and this attractive force energy that we have, we expressed in terms of Coulomb potential. So, here h square by 2 m nucleus, the Laplacian of the nucleus, minus h square by h bar square by 2 m the electron, the Laplacian of the electron, minus z e square 4 pi epsilon 0 r, where r is the distance between the electron and nucleus. So, we see how we increase the complexity of the problem, starting from particle in a box to hydrogen atom problem. Particle in a box and harmonic oscillator, they were defined as one dimensional problems. Particle in a ring, sphere and rigid rotor, we saw angular motion in that, and in case of hydrogen atom, how is it different from rigid rotor? It is different from rigid rotor is that in case of rigid rotor, the distance is between m1 and m2 is fixed. So, therefore, we had only theta and phi at the changing coordinates, but in case of hydrogen atom, we have r, theta, phi, all three are allowed to change. So, this gives us an idea about the Hamiltonians of the different models that we have discussed so far. Now, let us look at the once we have written down the Hamiltonian of this system, we of course would immediately go ahead and write down the Schrdinger equation corresponding to this Hamiltonian. So, we always had this h psi equals E psi problem that we have to solve. So, this is quite an important problem, where you see when we wanted to solve this problem, we have idea only about the Hamiltonian. So, this is rather general. Whenever we are solving a quantum mechanical problem, only information that is available to us is the Hamiltonian, whereas the wave function and the energy, these two are unknowns, and they would come out from this solution, from the solution of this equation. But we know when we have one equation, it is difficult, it is not possible to find out two independent variables, two unknowns. So, how do we get in all these cases? Because we have to remember that we first had this equation, that is one condition. The other condition we always invoked, there was always some boundary condition that the system obeyed. Using this boundary condition, so we have now two different conditions, and we think within that we could obtain two different unknowns, that is the wave function and the energy. What we do is now is look at the eigenvalues of these problems. So, for example, particle in a box problem, we had E n given by n square h square divided by 8 m l square, where m is the mass of the particle, l is the length of the box, and h is the Planck's constant, and n is an independent quantum number, where n goes from 1 to so on and so forth. Remember, n is 0, not allowed. We discussed why it is not allowed when we are discussing this problem. The other thing that you must notice is that the energy here depends as function of n square. Now, we would have more idea about to compare when we write them down, the other solutions. In case of harmonic oscillator, the energy that we had is h bar omega n plus half. So, here n goes from 0, 1, 2, and so on and so forth. Please note the difference. Here n equals 0 is allowed, here n is 0 not allowed. The lowest value of n is 1. So, therefore, the 0 point energy or the lowest energy available to the system is simply h square divided by 8 ml square. Here the lowest possible value of this quantum number n is 0. So, therefore, E 0 is your half h bar omega, and this is the 0 point energy of this system. When we went to the particle in a ring, we had this expression where the energy levels for particle in a ring depended on m square. So, here this has n dependence, this has m square dependence, where the values of m were 0, plus minus 1, plus minus 2, and so on and so forth. So, the lowest, so m is again the lowest value of this quantum number is 0, and the corresponding 0 point energy is 0. In this case, the particle is said to be at rest, that it is not showing any movement. The other thing that you notice here is that we have now plus 1 and minus 1, plus 2 and minus 2 energy levels allowed. So, that means while we would have same energy when m is plus 1 or m is minus 1, because you see the energy depends as m square. So, therefore, we have this degeneracy coming into picture, whereas particle in a one dimensional box or harmonic oscillator problem did not have this degeneracy. The degeneracy that we are experiencing in particle in a ring problem is the manifestation of the fact that the particle is now moving along x y axis on a plane, and there is a symmetry in this motion. Of course, we have converted this x y to r. So, therefore, we see only one we have expressed the Hamiltonian in terms of the spherical coordinates, where only phi is varying, where r is constant, but then we see that the circular motion that the particle shows goes around the x and y axis. Because of this degeneracy that is present in the system, we have because of the symmetry that is present in the system, our energy levels showed degeneracy. Going to the particle in a spheres problem. So, where E was given as L as a function of L, the energy levels came out to be, where in this case I and this case I is the moment of inertia given as m r square. M is the mass of the particle and r is the radius of the ring or radius of the sphere that this particle is experiencing. Alright, so here what happens? L, what are the values of L? L can be 0, 1, 2 and so on and so forth. For each value of L, we have m going from minus L to plus L in the step of 1. So, therefore, for each value of L, we have 12 plus 1 number of m values. So, we will come back to the degeneracy. So, in this case, the degeneracy of the levels actually keeps changing. So, the degeneracy is 2L plus 1 here. So, if we write down compare the degeneracy of the systems, degeneracy for particle in a box is 1, they are all non-degenerate level as long as we are discussing particle in a one dimensional box. Harmonic oscillator, one dimensional harmonic oscillator, we had energy levels non-degenerate. So, here for particle in a ring, the lowest energy level is degenerate, all other energy levels are two-fold degenerate. So, for each non-zero value of m, we have a plus m and minus m allowed. So, therefore, the degree of degeneracy is 2, and here for particle in a sphere, the degree of degeneracy keeps changing. For example, if L is 0, the degree of the system is non-degenerate. When L is 1, the system is three-fold degenerate and so on and so forth. So, while the first two cases they were non-degenerate, particle in a ring, only the lowest energy level is non-degenerate, others are two-fold degenerate. Particle in a sphere and similarly rigid rotor, their degree of degeneracy keeps increasing as we increase L value. So, rigid rotor solution closely follows the solution of particle in a sphere. So, we need not discuss them that separately. Then we come to the final problem, the hydrogen atom problem. So, the hydrogen atoms solution turned out to be where h bar mu is the reduced mass of the system, which is equivalent to the mass of electron. A is the Bohr's radius, which is a constant. So, you have this constant whose value turns out to be 13.6 electron volt, multiplied by Z square. Z is the nuclear charge, which is 1 in case of hydrogen, and divided by n square, where this n the quantum number. So, here n again 0, n equals 0 is not allowed, n equals 1, 2, 3 are allowed. Now, when we define this n, we also know that corresponding to an n value, we have L values which goes from 0, 1 until n minus 1, and for each value of L, the m values goes from minus L to plus L in the step of 1. So, therefore, for a given value of n, we have n number of L values. So, for n equals 1, we have 1 L value, that is 0. For n equals 2, we have two number of L values, that is 0 and 1, and for a given value of n, we have n number of L values, and for each L value, we have 2 L plus 1 number of m values. When we take them together, we see that the degree of degeneracy is n square. So, for n equals 1, we have 1 energy level, when n equals 2, we had 4 energy levels, and so on and so forth. Of course, this n square became 2 n square when we discussed the spin of the electron. So, this n square is when we are silent about the spin. So, we are talking about the orbitals. When we talk about the spin, that means the spin orbitals are the unit functions. In that case, it can become 2 n square. So, please bear this in mind. So, we say that the degree of degeneracy is an interesting function as we change our system. The other thing that we could see is that the dependence of the energy level on the quantum number. So, n square dependence, n dependence, m square, L into L plus 1. So, that you see that the dependence on the energy level on the quantum numbers also keeps changing, and here is a function of 1 over n square. So, here we saw the degree of degeneracy and the energy levels of the system. All right. So, if we now we would go ahead and discuss actually the eigenfunctions or the solutions of this Hamiltonian with respect to the wave function or the eigenfunctions of the system. So, we have again this is the equation that we solved. We discussed about the solutions that were coming out of the energy. Now, let us look at the wave function. So, the wave functions for particle in a box problem, we had 2 divided by L under square root sin n pi x divided by L, where we saw that the wave function is simply a sine function, and this term is the normalization constant. When we look at this some of the lowest and low energy eigenfunctions, we see that this is a sine function between 0 to L. So, when n is 1, we simply have the function like this. When n is 2, we have a function where we see a node appearing at L by 2. See, when x equals L by 2, we have this function becoming 0. So, therefore, a node appears, and as I go higher and higher energy levels, of course, I am not writing the energy levels. You should remember that energy level depends on n square. So, as we see that as we go higher and higher energy, the number of nodes are increasing, and when I draw the probability density, we would see that we have more number of waves coming closer, and as in the same way when you go to very large value of n, you would see that more number of crests and troughs in this probability density will be appearing closer. So, it will essentially show a classical motion for large value of n. Coming to the particle in a the harmonic oscillator problem, we had the solution to this problem was psi n given by the normalization constant multiplied by a Hermite polynomial of nth order and multiplied by e to the power minus rho square by 2. This Gaussian function multiplied by a Hermite polynomial of different order, for example, H0, 0th order polynomial is Hermite polynomial is simple 1, first order was 2x or 2 rho. So, therefore, this is a polynomial and this is a Gaussian function. When we plotted this wave functions, let us plot them in a harmonic oscillator potential, we would see that the wave functions actually, so the lowest eigen function, you would see that it has maximum value at x equals 0, rho equals 0. It goes down as a Gaussian function e to the power minus rho square by 2, but what we experience here, unlike particle in a box, the wave function actually leaks through this potential barrier. This is the process of tunneling, which is not seen in case of particle in a box problem. Why is it so? Because particle in a box, we have the boundary has infinite potential, but here we have a soft boundary. So, where the wave function actually tunnels through. So, when I go for the higher wave functions, I would see this feature. Coming to particle in a ring, so we had psi m as a function as e to the power I m phi, where phi goes from 0 to pi. So, for the first time we saw a complex eigen function. Of course, we can write it as a cosine function plus sine function. So, the energy levels will go as m equals 0 and non-degenerate, m equals plus 1 or minus 1, m equals plus 1 or plus 2 or minus 2, and so on and so forth. And this is how the energy level spectrum would appear for the particle in a ring. When I talk about the eigen functions, so of course, I have a real part, I have an imaginary part. So, instead of writing that in a ring, I am opening up the ring from 0 to 2 pi, and if I have to draw the real part, which is a cosine function, so you would see that this will appear something like this. So, at cos pi this will become minus 1, 0 it will become plus 1, 2 pi it will become plus 1. So, this is how the cosine real part of the solution looks like. The complex part, the sine part, sine function would look like this. So, now we have a sine function and a cosine function, and if I have to write down the probability, so psi m absolute value, you would see that I would have always 1 over 2 pi. So, because e to the power plus I m phi multiplied by e to the power minus I m phi, that will give me 1. So, therefore, the probability density is uniform throughout the ring. We discussed about this particle in a ring problem. When the next, when we discussed the particle in a sphere, which we used as the eigen function of the L square operator, and the eigen function of the L square operator are at the spherical harmonics. So, and we express the spherical harmonics in terms of these Legendre polynomials, and which are also with associated Legendre functions. So, multiplied by this phi term. So, we see that the spherical harmonics has two part, the s of theta, which depends on theta function, and then t of phi. So, this is a function of L and m, and this is a function of m, and with using this we could describe the spherical harmonic function, which is the solution for particle in a sphere or a rigid rotor. Now, when we go to hydrogen atom, the hydrogen atom problem was the most complex problem that we discussed. The total wave function now would have r, theta and phi dependence, which we discussed as a which has having two solution, one the radial part of the solution and the second one is the angular part. Now, the angular part is simply spherical harmonics. So, everything that we knew we use that. We were interested mostly in the radial part. When we looked at the radial part, we saw that it depends on n and L. So, the wave function and then in addition to the radial part, we also discussed what is r square, r n L square, r square, which is the radial distribution function, which gave rise to the beautiful shell model that we are so familiar with. So, so in today's lecture, we had a comparative discussion of all the quantum mechanical models we have discussed so far. So, we could see the relation between them, the differences between them. Thank you for your attention.